Multiplying radical expressions. I'll give several examples in this video. With multiplying radical expressions, what you want to remember is that you're always taking your free with free and your radicals with your radicals. And so when we look at this, I have this 5 that's free, and then I have an implied 1. So I can go 5 times 1 is 5. Now for me, I don't ever multiply radicals. Instead, I look for pairs. I see if I can get any groupings there. And so I actually break down these numbers. I know that 12 is 2 squared times 3. That's 4 times 3. And that 10 is 2 times 5. Now if you consider all these numbers all under the radical, I'm looking to see who gets out. And it doesn't matter whether I have 1 or 2 radicals. When I look at these, let's go back to the analogy of having jail. A lot of times kids will say, oh, school's like jail. Well, it doesn't matter whether you're in an English classroom or a math classroom. Jail is jail, right? So you're all in jail. This is one big jail cell, so to speak. And so when we look at this, we're seeing who can get out. This 2 can come out, and the rest of these numbers will stay in. So I can bring the 2 out, and everybody else stays in. So I've got a 3 times 2 times 5. I will not accept an answer like this because there's work left to be done. So you're expected to go through and multiply. So multiply your free values. So 5 times 2 is 10. And anything under a radical, the proper name for that is a radicand. So we look at the radicand numbers and we'll multiply those. 3 times 2 is 6. 6 times 5 is 30. So this final answer here would be 10 rad 30. Once again, the idea is that you want to take your free with free, and then your radical values, you want to break those down. Break those down as far as you can, trying to group up any pairs. You get your pairs out, and then whatever's left under the radical gets multiplied through, and you make sure that this is completely multiplied and simplified. So there's example 1. Let's do another example. So for example 2, I've got 3 rad 5 times negative 2 rad 20. I'll start the exact same way. I've got these 2 values that are on the outside. So I'll call this 3 times negative 2. If you want to go ahead and call it negative 6, that's fine. And then with my radical numbers, I'm just looking at how I can break these down. I know that 20 breaks down as 4 times 5, or 2 squared times 5. But then I've got this 5 over here, which means that that would be a pair of 5s. And so as a radicand, I have a 2 squared and a 5 squared, meaning both of those numbers could get out, and that would satisfy all of the values under the radical. So if I bring the 2 out, it loses its exponent. I bring the 5 out, it loses its exponent. There's nothing left in the under the radical. And so if you talk about the square root of 0, square root of 0 would be 0, but it's actually square root of 1. And the reason for that is this is 5 times 1. This is 2 squared, or this is, 2 squared times 5, which would be 20, times 1. If you remember back to our GCFs, 2 numbers are relatively prime because they'll always have a GCF of 1. So remember how when we did our GCFs, you could never tell me there was no GCF. There's always a GCF of 1. The same thing's happening here. You're always going to be left with a square root 1, and the square root of 1 is 1. So the jailhouse, so to speak, closes down, and then I could just multiply these numbers. 3 times negative 2 is negative 6. 2 and 5 is 10. Negative 6 times 10 is negative 60. So the answer to this problem is negative 60. Let's do another. We've got bunches and bunches of examples today. So when we're looking here, I've got a negative 1 times a 1, an implied 1, so that's just going to be a negative. I'm guaranteed to have that negative. And again, I'm looking at how this breaks down. This is going to be a 3. 18 is 2 times 9, which is really 2 times 3 squared. And then for the a cubed, I want to write that as a squared a. Why? Because the only thing I'm interested in is squares, to get out of a square root. This has an index of 2, so it's telling me to get out, to pass through the airport security or jail or whatever you want to call this, whatever analogy you want to use. It has to have that exponent of 2. So these two values could come out. This comes out as 3 and a. And then when we look at what's left, we have this 3, this 2, and this a that's staying behind. So I would call that square root 6a. Now in a previous lesson we talked about when you bring a variable out, you want to put absolute values around it when it's to an odd power. We're going to kind of let that fall to the wayside. As long as you know that that is a rule for the principal root, that all your answers are positive, I'm happy with that. We'll come back at a different time, a later time, and be a little bit more stingy about having your absolute values. Right now it's more important that you're just aware that it exists. So we've got 3 examples there of multiplying radical expressions. And I'm going to do a couple more quick examples. I know the video is going to run a little long today. So let's go to example 4. When you have a radical times itself, keep in mind, I don't multiply what's under the radical. I never multiply radicands. I look for their pairs. So it's a different kind of mindset. If we start with our free values, 1 times 1 is 1, and then I look at my radicand, a 7 times 7 is a 7 squared, and wouldn't that automatically get released? So I could bring that straight out and just call this a regular 7. Meaning that if you had radical 3 times radical 3, that's just 3. Radical 5 times radical 5 is just 5. A radical 11 squared, which means radical 11 times radical 11, is just 11. So that is something that you want to keep in mind. Any radical times itself is just going to become a regular rational number because it's just a square is what you're looking at. Let's move on to example 4. Now keep in mind it has to go free with free. Don't jump like in the last example where you just see the same number. They have to be both under the radical. So when I look at this, I'm going free with free. 2 times 1 is 2. Now as I look at my radicand numbers, I'm looking for pairs. 3 times 2, there's no pair there. But AA means that I actually have a pair. So I could write this. I'm going to go 6, because that's 3 times 2 is 6. A squared BC under the radical. As I'm looking at that, clearly I can pull that A out and everything else stays. And you ask, why did I multiply 3 and 2? Because I recognized that neither part was going to get out from underneath the radical, so I just went ahead and multiplied them. Made my work a little bit simpler. My final answer, 2a rad 6bc. And we'll do one last example here and then we're going to move to the next level in the next video. As I look at example 6, I've got negative 4 rad 6x times rad 15xy. So I've got the negative 4 on the outside. Now for this big radical, I'm looking for pairs. So when I look at 6, I recognize that it breaks down as a 2 times 3, and I got an x. The 15 breaks down as a 3 times 5, an x and a y. So as I'm looking at these numbers under the radical, I have pairs. I can say that I have a 2 and a 3 squared. There's my pair. I also have a 5 and then these x squareds. Xx is x squared. And then a y. At this stage, I can bring my square terms out where they're losing their exponent. Keep in mind, I keep stressing this, do not multiply. To me it's ridiculous to multiply 6 times 15, get 90, and then try to break that all down. It's much simpler to break the smaller numbers down and just search for your pairs, because that's the goal of a radical. And so since I have these squares, I'll go ahead and bring these out. Negative 4 times 3 would be negative 12. I'm bringing this x out, so those are all gone. And then under the radical, I'm left with a 2 times 5, which is 10, and a y. So I'll call that 10y. And that's how you simplify radicals when you're multiplying.